Okay, it's a very big and intimidating room. Anyway, thanks to you three for coming at this session. So I am presenting here this paper co-author with a group of colleagues from the Bank of Italy. And this paper deals with the problem of forecasting in a very uncertain period. So how to tackle the instabilities caused by the pandemic shock. This presentation has 6 chapters, and I'll start from the motivation. So as all we know, COVID shock disrupted the economy from both the demand side and the supply side. It was a perfect storm also for the forecasting models, for the most traditional and standard forecasting models based on mean reversion, basically. So our question was how to adjust the forecasting models in a central bank to cope with these instabilities. And we deemed reasonable disentangling the common macroeconomic, proper macroeconomic common factors from the pandemic common factors, which is another source of commonality between the macroeconomic indicators, but has nothing to do with the macroeconomic stuff, right? We think that the scenario analysis is a very useful approach for policymakers to envisage the possible developments of the pandemic and of the related developments of the macroeconomy. So let's glance at the literature very briefly. The COVID shock triggered a very rapidly flourishing literature around the stuff of forecasting, the problem of forecasting in face of these huge instabilities. In the literature, we have many examples of studies and papers like Antolin Diaz and co-authors, where they treat explicitly the pandemic shock and include non-linearities in their model by drawing from the literature on stochastic volatility, macroeconomic risk forecasting, and time-varying coefficient models, and so on. Foroni and co-authors just use a combination of Midas and unrestricted Midas models and adjust the forecasting by using the forecasting errors made during the global financial crisis. Lenz and Primiceri and Tambalotti defined this synthetic COVID shock by combining macroeconomic shocks and tilting its propagation to take into account the pandemic shock and the fallout on the economy. And we decided to follow this stream of literature, and in particular the paper by Serena Eng, 2021. These authors have in common the fact that in their model they put in the same model the epidemiological modeling with macroeconomic modeling, and they exploit the interplay between these two forces to try to improve the forecasting performance. So our approach is the following. We combine macroeconomic and pandemic indicators, and we adjust a mixed frequency dynamic factor model we use at the Bank of Italy at ECB for the short-term forecast of GDP growth, quarterly growth. It's a 3-step procedure, basically. In the first step, we estimate the regressors by adjusting the standard common factor models augmented with the pandemic common shock. We then now cast and forecast one step ahead the quarterly growth of GDP for Italy in this paper. And finally, we envisage a scenario-based analysis. We set up a scenario-based analysis where we use a susceptible infected recovered model, very common in the epidemiological literature, to forecast 3 possible scenarios of the evolution of the pandemic, and depending on these, we project 3 possible macroeconomic scenarios in terms of GDP growth. And we use a Kalman filter, both to estimate the end of the sample missing values, because we run this model in real time, pseudo real time, and to make the predictions. So this is a quick look at the indicators. So we use a basket of macroeconomic indicators, very common: industrial production for Italy, for Germany, an indicator on consumption, and we use the payment data, which are largely used in the central banks in the very last period, because they are high frequency indicators, very timely, and they work very well in forecasting. And we have a basket of epidemiological indicators. The one we choose to include in our model is the number of new infections. We tried a combination of all these indicators: new deaths, new hospitalized, new infections, and this stringency index built for the Italian economy. But in the end, the best performer in terms of forecasting was this indicator, new infections. And this is consistent with ENG results. So this is a very standard model. I will be very quick on this. The difference between the observable variables X and their historical mean can be explained by 2 independent components: common factors and idiosyncratic factors. And we model the common dynamic factors as an autoregressive process. The dynamic factor model post-COVID is augmented with this guy here, which is the common pandemic shock, is the pandemic common factors. And these are the assumptions we make. VT is exogenous and is equal to 0 before the COVID, and to pandemic process, let's say, after February 2020, which is the date of the outbreak in Italy. And of course, economic and pandemic shocks are serially and mutually uncorrelated. And we define this small V hat, which is the pandemic shock, equal to the log difference between times T and T minus 1 of this V hat T, which is a pandemic variable, new infections in our case. And so we pre-treat the observable variables and we get rid of the pandemic effect from their dynamics. So they mean the observable by using the historical average before the COVID, and by using this particular average, mu1, after the COVID. And mu1 is simply the projection of the observables on the space spent by the pandemic process, basically. So in the second step, we forecast, we now cast and forecast one step ahead, this monthly growth rate of GDP. This is a mixed frequency model, so we have to breach the quarterly information, the quarterly target variable with the monthly indicators, and we recover the quarterly growth rate by using Mariano and Murasawa equations. We cast all this model in a state space form to be estimated by using Kalman recursions. We use an expanding window in pseudo real time. The first vintage we use is August 2020, and we are careful to replicate the missing values pattern at the end of the sample, of course. The first nowcast is 2020 Q3, and the first forecast is 2020 Q4. So we use this SIRR model, which is modified to take into account the coexistence of different variants of the virus, availability of vaccines, and stratification by age classes and regions. And we use in the model this Oxford Stringency Index modified for the Italian economy by taking into account the measure adopted locally by the local governments to tackle the spread of the virus. And we predict, this model predicts jointly both epidemiological series and the restrictions from the governments. So it exploits the interplay between these two contrasting forces, okay? This scenario analysis is envisaged depending on the spread of the Delta variant, because this model was built last year during the summer. And this chart shows the three scenarios. The baseline one is the blue, the most severe is the red one, and the most benign is the green one. These are the projections of the SIR model of new infections and of this stringency index. And based on these projections, we set up our macroeconomic scenario analysis. So let's come to the results and let me conclude. Our forecasting models performs very well if we compare it to very robust competitors like the forecast by the Bank of Italy and ECB themselves. They are very hard to beat competitors because they are based on both econometric estimates and judgments of the analyst based on very up-to-date information. So it's not so easy to beat these competitors, but our model performs quite well in terms of forecasting, in terms of nowcasting and nowcasting as well. But in this last period, because in the first 3 months of 2021, vaccination rollouts began, and our model was a surprise to the upside in forecasting GDP growth in Q2, so during the spring of 2021, because the vaccination rollout and somehow put a break in the relationship between the pandemic and the macroeconomic indicators, as we know, up to the vaccination availability. Let me move to the scenario analysis. Here are the forecasts for GDP growth in 2021 Q3. And this is the forecast we make in July, in August, and in September. We observe a gradual downward revision of our forecast. The bold line here is the forecast of GDP based on the baseline scenario. A gradual downward revision of our forecast was due to the worsening pandemic scenario during last summer due to the Delta variant spread. And the final figure for Italy was in Q3 was 2.6, so very close to our projections based on the most severe scenario of this epidemiological model. So this, let me conclude. I hope to be on time. The paper investigates whether including taking into account explicitly the pandemic variables helps to improve a very standard and common dynamic factor model to tracking better GDP growth during a very unstable and wobbling period. The performance of our model is comparable with very strong competitors. So the following caveat is in order. A more formal assessment of the forecasting performance needs more observations, of course, and we had not these observations at the time of the analysis. There are a lot of possible extensions. So we see two ones here. This model can be used to draw a comprehensive picture of the economy by forecasting also GDP components from the demand side and supply side. And it can be extended to other economies. That's it. Thank you for your attention.
Thank you for the talk. I'm Attila Baan from it's not at all my expertise. Is it?
Yeah. I hear you.
Yeah. So you mentioned that as soon as vaccination came online and basically broke the team of your model. Do you see any other factors, for example, the lack of testing after, I don't know, 1 or 2 years, the testing rate, many countries are already lower, which can further degrade performance end of the pandemic? And can you include that in your model to then potentially or further pandemic?
Okay. Yes, thank you for this interesting question. Of course, it's possible, even if this methodology is meant somehow to control for the possible instabilities that you may encounter during the time. Of course, in that particular quarter, it was the first quarter in the relationship between a pandemic and economy, macroeconomy, okay? So it was difficult for the model to grasp this change in real time. But in the following quarters, we have shown that our model somehow was back on track to anticipate maximum 1 quarter ahead the GDP growth, like in the scenario-based analysis I mentioned.
I would like to ask you, because you mentioned you use SIR model to like estimate or use the dynamics of the pandemic, but have you used only as a whole COVID pandemic, or for each of the wave have you used separate SIR?
For these projections are based and are focused on the Delta variants, only Delta variants, and it takes into account all the determinants which may affect the spread of these variants, from the vaccination to temperatures to the ages of people. Some of these characteristics are quite general, so they are useful to model the spread of any variant in principle, but the model is actually based on the Delta variant.
Right, perfect, thank you.
Thank you to you.
I also don't really know. Maybe there is a his report. I can copy it on desktop. I think so. I think we don't need support, but let's see. Okay, yeah. Hello, everyone. My name is Daniel Ahmadi. I'm a PhD student of Concordia University, and I'm going to talk about this two-step short-term electricity demand forecasting based on generalized additive models. It's called GAMS. It's a joint work with Armin Pourkhanali and Gordon Vassil. First, I want to point out that I am not going to talk more mathematically about the models, just I want to show some algorithms by charts and tables. In the first section, I'm going to talk about some motivation and the previous literature about the demand forecasting and the proposed models. After that, we are going to discuss about the data and modeling, and the end of the presentation, we have some results to show the output of the model. Okay, just briefly, I want to say that electricity demand is very important for governments and utilitize companies because they forecasting of the electricity can help them to purchasing and generating electricity and switching the electricity load in the network, and also it's help them to develop the infrastructure and the network between the different states of the country. And why we choose the Australian market, electricity market, and why we choose the Victoria State, because there are some evidence that the price of the electricity in the Australian market is much higher than other countries like EU countries and US. As you can see from the bottom line chart, it shows that the price of the Australian market is much more higher than the EU market. The right chart is the logarithmic one, and if you compare the logarithmic prices with the European zone price, you can see that the price is much higher, and there are also some spikes in the price. That is because of the nature of the market, of the Australian market, because you can place your order in the just 10 minutes before the price matching. So it's more dynamic in compared to US market that you place your order nights before. And Victoria State cover a considerable area of the Australia, and the market, I think it is the second main market in Australia to providing the electricity. Here are some most important driver for demand. First, if you attention the left-hand side charts. The top one is the pattern of the electricity demand. As you can see, that there are some smooth pattern in the demand, except in the end of the year and the first of the year, there are some noises. The second chart shows in detail these volatilities in 2017. And the two last charts are the humidity and temperature pattern that they behave conversely or mostly. And in the right-hand side, you can see the scatter plots between the demand and temperature and demand and humidity, and you can see that there are some nonlinear relationship between demand and temperature. We use this parameter as a main variable to modeling our forecasting. There are some proposed model in the literature for forecasting short-term forecasting electricity demand, that we can classify this into three main categories. The first one is the regression models that use GLM, GAMS, and decision trees and quanti-regression. And the second is time series and econometrics models that especially focus on ARIMA models, GARCH models, and some long-term relationship between demand and macroeconomic parameters. And some soft computing model like neural network and machine learning approaches also used to forecast the demand. It's the model that we use and the algorithm, the data that we have used in this model is the half-hourly demand for, I cannot see here, the 158 zone substation and one total demand and one forecasted value for evaluate for a benchmark to evaluate our models. And also we use the half-hourly meteorological data provided by Australian Government Bureau Meteorology, that is 132 time series related to temperature and humidity, and in addition their forecasted value. We consider three sets for training and validation sets, and also one set for testing the result of the model. We focused on generalized additive models, and the next slide I will say that why we choose the generalized additive models. For this kind of models, we examine various predictor combination like 1 and 2 step estimation of linear, smooth, or with and without interaction between the predictors. So there are many models to evaluate, and the variable selection procedure is completely different from the conventional approaches like feature selection, for example, forward selection or backward selection, because we want to examine the interaction between all of the predictors. So we use 6 different critical date times to train our model for 66 times 66 times 158 models. That is really huge fitting for the model, and compute the mean absolute percentage error median for each of these 6 date time, and rank the MAPE, and after that we select the first N model that have the lower MAPE. And if there are some the same variable, we combine that variables. And finally, we test selected model with the test set. And why we choose GAM model, we just briefly, I explained it. We examine 17 models that use the GLM, GAM, and SVR and trigonometric models in different feature selection approaches and feature extraction approaches. And finally, we saw that GAMs perform better rather than other models. So we are going to model the forecasting based on the GAM. Finally, we reach this model. Is the 2-step model. The first line is the demand, that is the T stands for time T, that is 48 time, intraday time, and D stands for the day, and T, H, and Z are the temperature, humidity, and zone stations. I don't want to talk about it a bit more, but in the first step, we model our demand based off the first line, and after that, we use humidity and temperature of the weather station that are close to subzone stations to model the subzone station demand, and use that subzone station demand. This one, if you can see, we use this demand to forecast the total demand of the Victoria State of Australia. This is just a picture that shows the weather station in the Victoria State and the subzone station, and we map the closest weather station with subzone station to model in the second step. Here is the main result that we find that if we group first 5 model or first 20 models, we can obtain a lower mean and median error in our model. And in the bottom line chart, we can compare our result with the forecasted value of IMO, that is the regulatory of electricity market of Australia. And as you can see from the left bottom chart, our model beats the IMO forecasted in most of the day, but some days our model perform weaker because we have lack of data for some holidays, especially for 24th of December and 25th of December. And for the intraday, for example, for December 5th, you can see that our model performed better than IMO. And here is the relationship between closest weather station humidity and temperature with subzone station demand. In the contour plot, it's better to show that for the low humidity and the low temperature, there are a negative relationship between the meteorological variables and subzone station demand. And for the higher temperature and the humidity ratio approximately 40, there are a positive relationship between humidity and temperature and the demand. We can see the same result for the relationship between the temperature and total demand, humidity, and total demand. For the temperature, you can see here that if the temperature increases, it will affect positively on the total demand. And for low temperature, it's just kind of positive, but it will be negative and it will be increased. For humidity, for the lowest humidity, the impact of the humidity on the demand is negative, and after that it will increase to a rather positive number. And for zone station, we can see this chart that when the demand of the zone station increase, it has a positive effect on the total demand. What are the advantages of the disadvantages of our model? Is the advantage is that we improve the IMO forecasted value for electricity demand 25%. And this kind of models are interpretable because you can see the relationship between the weather conditions and electricity demand as well. And they are highly accurate and parsimonious because we find that the group of 5 models will be enough to predict the demand. And I think that we just use 6 predictor to in our model to forecast the demand. And this kind of model also are flexible for variable selection because you can switch and you can I don't know you can consider a lot of combination of the predictor to find a suitable combination of predictor for your model. And the disadvantages is high cost of computation because you should repeat a lot of you should train a lot of model to obtain a good forecast value. This is some references that I use in this presentation, and thank you for your attention and for your time.
We have time for one quick question.
You're welcome. Yeah. Sorry.
I think I closed the window and said so.
Okay, yeah, that's fine. Yeah.
Cool, thank you. Right. So let's start in 1 minute. Okay, thanks everyone for coming for sticking around till the last session, till the last talk. My name is Hussein Kazmi. I'm working at the University of Leuven in Belgium, and this is joint work with my colleague Maria Paskevich, who is a data scientist at Activision Blizzard. So the focus of the talk will be on how to incorporate downstream task-specific information into forecasting models. It's not going to be heavy on the math, but we will take more of a general overview of things. So a quick outline. I want to start off by talking about the different workflows that are involved in the forecasting and decision-making processes. Then I will briefly cover 2 different example cases, one from the energy sector, one from the retail and e-commerce sector. And then finally, we will conclude the talk with some insights and work for the future. So if you think about a common decision-making workflow, this can range from anything in logistics to energy to retail. You normally have a data generating process that's generating some observations that you then fit your forecast model to. And then you use that forecast model to basically form part of a decision-making tool, which then allows you to create a decision for the future or a plan of action. However, if you think about this in slightly more concrete terms, then you have a disaggregation of the problem into 2 different streams. On the one hand, you have the forecaster's focus, which is really to minimize the mean absolute error or some other metric for your prediction task. And you have a second separate task, which is the decision maker's focus, which takes as input the forecast that was made by the forecaster, and then plugs that in to optimize for some metric of interest. This can be, for instance, sales, profits, what have you. More concretely and slightly more visually, so this is what's normally happening, that you have a business as usual scenario where you have some downstream costs. This can be the cost of procuring certain objects or the profits that you have at the moment or something like that, which you would like to optimize because that's the essence of the decision-making process. And then you assume that what would happen if you had access to perfect information about the future. That leads to some downstream costs, which basically identifies how much room do you have for potential improvement if you start to make tweaks to your forecasts and the decision-making that you do. This also introduces a second dimension, which is the forecast error, which is perhaps what we are more familiar with at the ISF. But that also leads to the idea of baseline forecasts, because now at this point you can already ask the question, like, where is the baseline forecast? And in some cases that is better than business as usual, that you can just plug in a very simple naive forecast, and that already allows you to do better than your baseline business as usual scenario, which means that the room for actual improvement is often in reality smaller than what you would assume, or the one that we saw earlier. And at this point, you can start to think about what other types of forecast models can you fit to your data. So this ranges from statistical and empirical methods all the way through to machine learning models. You can also start to look into the value of different types of forecast features. Like, for instance, if you use one set of features versus a different set of features, is that going to make any difference to your forecast error? But also, how is that going to affect your downstream processes? And then you can start to make decisions about whether those are actually bringing any value to the things that you're actually interested in or not. At this point, however, you can also realize that what you're improving for is not necessarily what you're interested in, because as forecasters, we are basically moving along the x-axis, while as decision makers, we have to think about the y-axis. So there is a fundamental disconnect between the two. And in certain instances, as we will see later, these can be correlated, but there are not necessarily any guarantees. And just to hammer down that point, the most accurate forecast is not necessarily the most performant forecast that you would be interested in. So a couple of quick example use cases. The first one is going to be from the energy sector. The second one is going to be from an e-commerce or retail sector. So we'll take a look at how these things really play out in practice. So you have probably seen these news articles recently flying everywhere. So basically that electricity prices are going through the roof. And if you are a householder or a business owner, then this is like quite a dangerous time to be alive, because suddenly your electricity bills have gone through the roof without you doing anything different about it. So if you want to minimize the electricity bills or the amount that you're paying for your electricity, then you can think about it as an optimization problem, where your decision making is related to how much energy do you consume at any given time and how much power do you consume at any given time. So more concretely, the electricity bill for individuals and business owners is typically a function of three different things. On the first hand, you have the power costs, which is basically like, for the households, it's basically how much of a connection strength do you have? Do you have a single phase meter? Do you have a three-phase meter, or is it something else? And then for industrial or commercial users, this can often be billed as how much actual peak power did you consume during a given period of time. So it's necessarily something that is correlated directly to your electricity bills. So this is like our favorite joke at the department, that with great power comes great electricity bills. But yeah, that's just a silly aside. Anyway, so back to energy costs. So the energy costs basically translate to how much energy did you consume over a certain billing month. A billing period, which can be a month, a day, a week, a year, doesn't matter. And that's really like identifying how much energy have you consumed during that specific period. And then finally, there are also taxes, which basically is not really an optimization problem. So we cannot recommend optimizing for that. So let's look at the first energy case then. So if you have all of this information and you're trying to minimize the amount that you're going to pay for electricity, then the first and easiest thing that you can try to do as a business owner is try to reduce your peak energy demand, because that really defines how much electricity bills you are going to get. And one way to do that is through storage mechanisms like electric batteries or something like that. So instead of formulating this as a mathematical equation, this is just like an optimization problem which has been formulated in words. Then the constraints that we have for this problem include how much storage capacity do you have, and also how quickly you can charge or discharge that storage battery. And then finally, the control variable that we have in this case is how much are you going to charge the battery by? So that's basically the control variable. And this is like an indication of how the demand looks like through time. So on the x-axis you have demand, on the on the x-axis you have time, on the y-axis you have the demand. And then we impose this constraint Pmax, that your demand has to be less than at every given instance in time. And then what you can do is you can increase your demand using a battery during times when it's below the Pmax, and you can basically then discharge the battery at other times. This translates easily back into the decision-making workflow that we discussed earlier. So more concretely, you can take a look at the optimization part and the forecasting part. And for the forecasting part, we implemented a number of different forecasts using the Darts library. This ranged from persistence models all the way through to simple time series models, and then more complex machine learning models like, for example, LightGBM or other tree-based methods as well. It also included an experimentation with how do you see the effect of different types of variables. And then you can start to take a look at the variable selection as a problem for the downstream value that you're creating rather than just the forecast accuracy. On the other hand, for the optimizer part, we implemented this as this is a simple linear problem. So we just used Pulp, which is a Python library to implement linear or, well, convex problems anyway, in a decision-making framework. And then we basically ran the simulation with the actual observations, but then we also ran the simulations with the predictions that would arise from the DARTS library to see like what's the effect of these non-ideal forecasts that you can create for the future. And that led us to a plot that looks something like this after fixing a number of parameters. So what you see here is on the left bottom, you have the fact, or what happens if you already have the observation data for the future. So there is no prediction uncertainty in this case. On the other extreme, you have the naive weakly forecast, which is basically just like a very simple baseline forecast for electricity demand. It's theoretically the simplest you can do because you're just taking whatever happened the previous week and then saying that it's going to happen again this week as well. And then if you plug that into the decision-making framework, then of course you will get a performance which is hopefully worse than knowing the future, but also hopefully better than business as usual. So without you doing anything about minimizing your peaks. Which is indeed the case that the no control case, or where we don't really take any decisions, is actually much worse. So it's through the roof in this case, at least. But then there are also all these different types of models that we have built, and then some of them perform better than the naive model. Like for example, the linear model, which doesn't include any covariates. It performs better than the naive weakly model in terms of both the forecast error and also the downstream costs that we incur using this model. But you can also see that if we include a bunch of different covariates, like for instance, the temperature variables, the humidity in the system, for instance, calendar features like whether it's a holiday or not, all of these kinds of things, then in some cases you do improve your forecast error. And in other cases, it doesn't lead to an improvement in the forecast error either. But what you get at the end is that in most of the cases, this does lead to a reduction in the downstream costs. What's perhaps even more interesting is that the most accurate forecast that we got in this case was a light GBM model, which included plenty of covariates ranging from temperature and humidity to calendar features. But even though this was definitely the best model that we had in terms of forecast error, it was certainly not even close to being the best model in terms of downstream performance. So it was just like one of the worst performing models that we actually saw. On the other hand, a very simple theta model that does not take long to fit at all and does not really require any machine learning or covariates or anything else. If you fit that model to this data and then you use that as your input for downstream decision making, that already leads to the best performance that we saw, at least in this case. And that was quite surprising because, I mean, normally what you want to do with your machine learning models is that you want to improve the accuracy, but you also want to reduce the downstream costs of your optimization problem. Right. So just to reiterate, this thing that going from the naive model, here you see the forecast improvement, but here is on the y-axis, you actually see the roughly the task improvement that we can get, which is not necessarily perfectly correlated with the two. Even though the general trend is that more accurate forecasts do tend to improve the actual performance on the downstream task. But based on the model that you do select, there is no guarantee that this is going to lead to a positive outcome for your case. Then there are a bunch of different simulations that we ran for different types of storage, but I will skip this in the interest of time. Suffice it to say that the task improvement that you can get on these different cases is wildly different as well. So that was a very simple toy case where we just went with the power, the peak power on the system, but you can also make it a bit more interesting. And you can say that in addition to the peak power, I'm also interested in minimizing the energy costs. So now it becomes like a multi-objective optimization problem where you also have the peak, where you also have the constraints coming in from the peak capacity. And then you have also the constraints coming in from the battery storage. Everything else in the problem remains exactly the same as before. And what we see in this case is now it becomes even more complicated to understand. Well, it becomes a bit more complicated to understand, but on the x-axis, you still have the forecast errors. And on the y-axis, you have the peak violations, but now the size of each scatter point indicates how much money you have to pay for these particular optimization problems. And basically what we saw at the end was that despite the perfect correlation with increasing forecast accuracy, the models that you do end up choosing are perhaps not going to be the same as the ones that are going to minimize your downstream costs. So that's just like reinforcing the same idea as well. Then finally, to go through this very quickly in a couple of minutes, we also tested out a bunch of different cases from the retail sector. And this basically took data from the Walmart M5 competition, where we basically are trying to forecast the future demand for certain products and then see what happens if we apply different types of discounts to the sale, to the prices of those items, and how does that affect those sales. And then the idea is that our objective is to maximize the weekly profit by implementing a certain set of discounts on all of these products. Now, this is slightly more challenging or involved in the sense that we now have certain products, while previously we just had one specific product that we were interested in optimizing. Here too, we implemented forecasters using the DARTS library, and then we also implemented that optimizer using the Nevergrad library, which basically was used for the optimization task. And if you look at the aggregate performance, in this case, we didn't really end up with very good forecasts yet, at least anyway. But then if you compare the performance from the naive weekly to the fact, we again have a reinforcement of the same idea that while in general, as you improve the forecast error, the performance improves, but there is no guarantee that the best one in terms of forecast accuracy is also going to be the best one in terms of the downstream performance. So at this point, a couple of questions arise. The first one is, can we forecast a priori which models are going to do well on certain downstream tasks? And the second one is whether there is any way in which we can somehow incorporate this information directly into our forecast models. And I suppose in the interest of time, I will skip those. So yeah, thanks a lot. And if you have any questions, go ahead.
Thanks for the presentation. It's really interesting.
Thank you for the presentation. Really interesting work. So, what are you considering as next steps? So you had one slide. So, are you planning to incorporate some sort of like modify the loss function to tune it based on the downstream costs?
Yeah, so definitely, I mean, changing the cost, which was this slide here. So that's definitely one possibility that you can directly modify the costs. This also leads to certain problems, especially if those loss functions may not be differentiable, for instance. And then how do you backpropagate that information? So in that case, especially, it makes sense to have like a meta selector where you just like do basically the simulation that I was showing you earlier, and then you go for the forecaster that performs best. That's also one reason to do that, is because otherwise you are restricted to the same class of forecasters. While like we saw in this case, like the Theta model performs better than most other models, not necessarily in terms of forecast accuracy, but definitely in terms of the downstream performance. And then if you're focused on training a neural network, then perhaps you'll never get to the data model at all. So, yeah. Thanks. All right. If there are no other questions, then let's wrap it up and head off to Atibio. Thank you.